Let's think about the difference between the classical particle that's forced to live between a region, a one-dimensional region of space. As usual, let's say x equals 0 and x equals L, and let's compare it to the quantum description of that. So classically, right, a particle has an energy if it's free to move about in that region, it has some kinetic energy. And the more the speed, or the greater the velocity, the greater the kinetic energy. But the particle, right, all it does is, if energy is conserved, it hits the right wall, comes back, hits the left wall, comes back, and just keeps going back and forth at constant speed. And it's therefore it can be found at any one location, right? But that's not the case quantum mechanically. So if we look at the eigenfunctions, let's say psi 2 of x, right? So if this is L, the function goes to 0 here, and it goes to 0 at 0, and it also goes to 0 at the midpoint. So at L over 2, the function goes to 0, and so the probability, which is psi star psi, is just psi 2 of x squared, and of course that also goes to 0 at L over 2. So, so this is true for, if we look at psi 3, that's an even function. It has places, right? It has nodes, and as we increase n, we get more and more nodes, and therefore more and more places where the particle cannot, at which the locations of which the particle cannot be found, right? So you could say, well, that's sort of a feature of eigenfunctions, and eigenfunctions have no time dependence, and so it's not quite a representation of the real world, a particle that's dynamic and moving around. But if we take superposition, right, and we do, we make a superposition, let's say, of n equals, I don't know, 1 to 9, but n is only odd. So odd values of n, we can choose psi n's. Right, then we have that for the state, or we could change that number. Let's just make it n to, I don't know, some number m. That's also odd. And then we only have odd functions. Well, all of these functions go to 0 at the midpoint, right? And the greater the n is, the more nodes it will have. But all of these functions will share the fact that the psi n, all psi n's have this feature. And so quantum mechanically, it's clear that when we look at the probability, right, it's going to be built out of these functions. We're going to square function, but all these functions, all of these terms in the probability, right, let's consider that quantity. It's going to have multiple squared terms, but all of these terms go to 0 at L over 2, and then cross terms, but cross terms are made out of terms that go to 0 at L over 2. So we can certainly see without too much trouble that the particle P of L over 2 is 0. Particle cannot be found at that location. And that's not a feature that we find classically. But of course, this is the quantum world. But of course, it also has to be true that for high, as n goes to infinity, then we need to be able to recover from this formalism, from this kind of a thing, the idea that we described at the beginning, where the particle can be found anywhere between 0 and L. And we'll see that.